me record this class. Class is being recorded now. And Albert, you can go first.
Okay. Let's see, you could see it?
Yeah.
Okay, so this is 15.1 modified. So the question is, so over there it says in problems 1 to 3, determine if x equals 0 is an ordinary point, a regular singular point, or an irregular singular point. So I did a variation of the first one. So x squared, I mean, it's really a variation of all of them, but x squared y double prime plus x parentheses x squared plus 1 close parentheses y prime plus, instead of 2, I have 3y equals 0. And we need to see if x equals 0 is an ordinary point or a regular singular or irregular singular point. So what we did was in the beginning, we have to divide the whole thing by x squared, right? So we could get it into this equation that we could check if x equals 0 is analytic or not, with p of x and q of x. Right? We have a of x y prime plus b of x y, sorry, a of x double y double prime plus b of x y prime plus c of x y equals a of 0, and we divide by a of x. So this is x squared here. That's why we divide by a of x. And then we're supposed to get, I'm reading from the notes on page 2 of day 15 in front of me. And we're supposed to get y double prime plus capital P of x y prime plus q of x y equals 0, where P of x is B of x over A of x, and Q of x is C of x over A of x. So in our example, I divided everything by A of x for us to get P of x and Q of x. Right, so we got y double prime plus x squared plus 1 over x, y prime plus 3 over x squared y equals 0. That means that P of x, capital P of x, is x squared plus 1 over x, and capital Q of x is 3 over x squared. Now what we do is we need to check if it's analytic at x equals 0, but we need to do that for lowercase p and lowercase q of x, and we have to rewrite our equation that we had before into a different form of y double prime plus lowercase p of x over x times y prime plus lowercase q of x over x squared times y equals 0, where p is equals x p of x and q lowercase q of x is x squared q of x. And so over here I got lowercase p of x equals x capital P of x. So that makes p of x, the lowercase p of x, x squared plus 1. And lowercase q of x, once we take out x squared from it, meaning once we multiply by x squared, we get 3. And both of these points can be valid, meaning they are analytic at x equals 0. So that makes it a regular singular point. Thank you.
Okay, why the what can like what make how do you make the conclusion x equals 0 is a regular singular point? What's the reason?
Since they're both analytic, they're both analytic at x equals 0. Since they're rational functions where denominators are not 0 at x equals 0, that makes them
okay. Why both of them?
analytic.
How do you know both of them are analytical at 0?
Because when I plug in 0 as x into x squared plus 1 or into 3, which has no x, then
right.
I get
so
an answer.
It's better. Right, you can write one more step in between. That p of x, the little p, the lowercase of p of 0 equals 1. Little
right.
lowercase p of x equals
and
3.
Q, oh, right.
Right. Okay.
I thought, right, you're right. I thought it was obvious because you don't need, I mean, it's not such a complex problem to plug into 0 to it.
It is obvious, yeah. But
yeah,
I just want to ask you.
But definitely important. Yeah.
Okay.
Thank you.
Okay, then 2 from Moses, 15.2, then David 5, Jun E 3, And Katarina, her own question. We'll follow the order in the chat.
Hello, can you see it?
Yeah.
Okay. So this question is similar to the last one where we have to find out whether x of 0 is an ordinary point, regular singular, or regular singular point or an irregular singular point. And so with that, first of all, I just wrote out the equations little p of x equals to x times big P of x, and little q of x equals to x squared times capital Q of x. So first of all, we have to divide a by the whole equation. So in our case, a of x would be 1 plus x squared. So we have to divide it in every single one. So our new equation would be y double prime plus x times y prime over 1 plus x squared plus x squared times y over 1 plus x squared equals 0. And so using the equations for p of little x and q of little x, we find out that they are equal to x squared over 1 plus x squared, and q of x would be x to the fourth power over 1 plus x squared. And so to find if they're analytic, in my case, I had to find the limits as x goes to 0 from positive infinity. And so we find out that both of them are going to be 0, which means that they're both analytic, making x equals to 0 a regular singular point.
Okay. I didn't see the regular.
Yeah, I forgot to write it down, so that's why I just said it here.
Okay. All right. Thank you. If anyone has any question, feel free to jump in at any time. All right, David.
Okay, so I'm doing question 5 from homework 15, and what I'm told to do is find two linearly independent solutions for x greater than 0. And so we kind of do what we just saw was done by Moises and Albert. You need to find the little p of x and little q of x, and this is done by dividing underneath that original term, under the p under the q and the r, and that will give you this new equation, and then from that you can take the second term as p, third term is little q, and then you multiply it by x and then x squared, and then you plug in zeros and you see what you get. And because what we have here at x of 0, we have a regular singular point, right? They're both analytic at x equals 0. We can assume that we have a Frobenius type solution. And so I made a little bit of a mistake here, so we'll just ignore that. I was doing the wrong thing. So just start from where the arrow first starts and points to the next line. So what I do here is I plug in these certain series as solutions for y, or stand-ins for y, or whatever you want to call them, and then I plug them into the equation. So we have the 4x, and then the series of from n equals 0 to infinity, summing up from, of n plus r minus 1, c of n. And then I do the same thing with, y prime and just y. And so the next step after that is I need to put in the x into my equation, the first term of my equation. So I'll scroll to the top, it's in that line. I put in the x, and notice how the x goes from n plus r minus 2 to n plus r minus 1, because there's an extra factor of x that's now in there. The same thing happens for the, oh no, that's it. Yeah, just that time. And so what happens now is I do some math, and I am basically combining all the terms inside of here because you'll see why I need to solve it so that I can get a certain equation, and so that I can solve this series. And so I do some math, and I actually, I readjust my indices because I need to get x to a certain power. I need to match up all the powers. And so I adjust from n equals 0 to n equals negative 1 as the beginning term, so that I can go from x to the n plus r minus 1 to the 2x plus r to x to the n plus r, sorry. And then so Now, the problem with this is that now we have summation starting at n equals -1, and we can't have that because then we can't get rid of it and get a nice equation equaling 0. We'll still have sums in there. So what we have to do is we have to take out the terms for n equals -1, and then this will allow us to take the original sum and just set n equal to 0, and then we'll be able to have that nice x to the n plus r. And so that's what's happening here at the bottom of the page. The same thing has to happen for the first and second sum. And then the things that are circled here are the terms at n equals -1, the two things that are circled here. And so after that, I didn't realize I didn't need to do this. What I actually did here was solve for values of r again, when I already had them from the beginning right over here, right? So that was unnecessary, but the math that I did to get there actually was very helpful, because right now you'll see that I have to find out what the solution is for r equals 1/2 now, or the p of q or q of naught, or whichever one it was, right? And so I plug it into the equation that I had. It cancels out nicely with these n equals -1s over here in the equation. I don't know if it's necessary, but I plug it into the rest. I do a lot of math. I factor out everything out of here. I try to get this nice x to the n plus 1/2 out of there. And then I find the recursion relation. It comes out to be c of n plus 1 equals -2c of n over 2 of n plus 3 times n plus 1. And so I wasn't able to find an exact c of n equals, c of naught, whatever, like that general equation. The numbers were kind of dicey, but I was able to put up a basically what it would be. That's the last term is like what generally you'd have for each term, and so that's the first solution. And basically we're going to do it all again for r equals 0. It's a little easier this time because the 0 gets rid of a bunch of stuff. Actually not that much, but a few things. I find my recursion relation. I plug in a couple numbers. I think that's the general term, very similar to the last, not really. And then, yeah, so that's my second solution. So yeah, that's it.
Okay, very nice. A lot of math. All right. Okay, so Katerina.
Okay, give me a second. My internet is really bad though, so.
Oh, okay.
Yeah, apologize for that.
Oh, it's okay.
Let me know if you can see it, please.
Yes, it's up.
Awesome. So I did my own question, and the question that's being asked is determine if x equals 0 is an ordinary point, a regular singular point, or an irregular point. So I chose this equation x squared in parentheses 4 minus x y double prime plus in parentheses 6x plus x to the power of 3 y prime plus 3x minus 1y equals 0. So the first thing I do, I check if it's a singular point at x equals 0, and we see that it is a singular point, since when we take the x squared in parentheses 4 minus x and we plug it in the x, and when we plug in the 0 into the x, it gets a 0. And then when we take 3x minus 1 and we plug in the 0, it does not equal to 0, but it just equals to -1. So this equation is in the form of a of x y double prime plus b of x y prime plus c of x y. And what I did is I divided by a of x, which would be x squared form in parentheses 4 minus x. And I also factored out the x from the 6x plus x to the third power. So like I could simplify it a little easier, and then I simplified it by x, And then what was left from it is y double prime plus 6 plus x squared divided by x in parentheses 4 minus x y prime plus 3x minus 1 and x squared in parentheses 4 minus xy equals 0. And then I simplified a little more, and I wrote it here on the side when a divided by b divided by c is the same as a divided by b times c. I mean, I could have skipped that step, but I decided to do it because that's how it was explained in the lecture. Yeah. So when we do that, I have y double prime plus 6 plus x squared divided by 4 minus x divided by x y prime plus 3x minus 1 divided by 4 minus x divided by x squared y equals 0. And then since we simplified it, our little p of x would be 6 plus x squared divided by 4 minus x, and the same with little q of x equals to 3x minus 1 over 4 minus x. And then we know that it's analytic, and those are rational functions because when you plug in 0 into the x, the function does not equal to 0, so that's why it makes it a regular singular point. Thank you.
Hold on. Hold on.
Yeah.
Okay, let me ask you a question to clear your mistake.
Yeah.
When we see functions analytic, what does it mean to you?
I mean, it means that they're not equal to. They're not equal to 0, and we can evaluate it at 0.
Right, we cannot. Right, it cannot be represented by a power series at the point.
Mm-hmm.
So in this case, if you plug in 0 into it, you have no problem. 0 does not. So 0 in the basically 0 in the domain of p, little p, 0 in the domain of little q. So that makes them analytic. It's not because they equal to 0. Functions equal to 0. That's no problem.
That's true. Okay. Yeah.
Yeah.
I understand.
Maybe
I should have explained a little more. Yeah.
Okay. So all right.
Thank you.
You're welcome. Thank you. Okay, Junyi, question 3. Yes, Shu Xian, unless you change 3, change something in question 3, you can do that.
Okay, so I'm presenting question 3, so which is the same solving problems, but with different power degrees, I think. So I just got like a x cubed times a 1 plus x squared times a y double prime plus 2 times the 1 plus x squared times the y prime minus 6x times 1 minus x times y equals to 0. So we divided the x cubed times 1 plus x squared, and the p of x, which is equal to 2 times the 1 plus x squared over x cubed times 1 plus x squared. So I can cancel it out, and which equal to the 2 over x cubed. And the capital Q of x is equal to 6 times the 1 minus x over the x squared times 1 plus x squared. So I can plug in the x equals to 0. So the capital P of 0 is undefined, and the Q of 0 is undefined also. So they're not ordinary since they're not analytic at x equals 0. So the lowercase p of x, which is equal to the x times the capital P of x, equal to the 2 over x squared, and the lowercase q of x is x squared times the capital Q of x, which is equal to 6 times 1 minus x over 1 plus x squared. And I plug in the x equals to 0 again, so I got the p of 0 is undefined, q of 0 is equal to 6. So since they're not both analytic at x equals to 0, so then they're irregular singular point.
Okay.
Okay, thank you.
Thank you. Shu Xian, you want to do a different version of 3?
Oh no, because I prepared like a 15 like 6, but I cannot finish, so that's why. So I don't have time to finish. So
Okay.
so I only like did like half, so it's not complete. So that's why I don't want to present. It's only half. Okay. Thank you.
You're welcome. Thank you. Oh, we finished the for business. Anyone has any questions? Otherwise, we're going to note 16. Okay, Suxian, you raise your hand. You have question?
Oh yeah. Maybe I just missing somebody present like 15 like question 2. There like a small p x like on the top have like x like a power 2, but if you plug in like x is equal to 0, is like a small like a p x is equal to 0. That's like a regular singular point or irregular singular point.
Hold on a second. So you're talking about 15.2.
Yeah.
I remember it's regular singular point because.
Oh, okay. But yeah, I read the note. You said that's like a denominator. It's like a small px, like is not equal to 0. That's like a called regular single point. But if like a no, I confused. Okay, it's equal to 0.
No,
that's
right. You're right. If the lowercase p, lowercase q, the denominator is 0, means that not analytic. Means 0 is not in the domain of those two functions.
Yeah, only like it depends on denominator, so it's not on the top, right?
No, not for the numerator, the denominator.
Okay, I got you. I did right. So that's why I want to just make sure, because I don't want and then to have a different point. Okay, thank you.
You're welcome. Okay, Jun Yi has a question too. Question 7. 15.7. 17.7. Yeah. Oh, okay. You scared me. You're already on 17. Okay. 15.7. Find two linearly independent solutions. So 7, 3x squared. Well, so Junyi, can you do 5 and 6 or 8? So you can do 5, 6, and 8, not 7? Or what's your question? Yes, David.
Yeah, I was having trouble with this one too. I'm not sure because as part of the question, one of the terms, what is it? Yeah, the second term of the y prime, it's gonna have an x squared going into it, right? Because the x is gonna factor in with the x. And then what happens is that you end up having to make n equal to 1, and then it's kind of weird. So I'm not sure what to do there because like it's like, how do I present this series? Because I need n equals 0 up to n equals infinity, but then I can't shift it down, you know?
Oh, can you show me what you did? Then we go from there.
Sure. Here, I'll actually just present again. It's on the 7, right? 6, 7. Yeah. So I was stuck over here because you plug it, you find your r's through the characteristic equation, the Frobenius thing.
1 and the negative 1/3.
Yeah, and then so I'm trying to, as you can see, I plug in the normal y double prime series, right? And then it's the second term, it's the x parentheses 1 plus x, then the y prime. And then what happens is that the x squared, see here, it's the third term from the left in the second to last line. You have that series of n plus r, a to the n, x to the n plus r plus 1, because the x squared goes in. See, it goes from n plus r minus 1 to n plus r plus 1. And so what I did last time, as you saw, is I just took out one of the terms, right? Because I could just take out when n equals -1. But here, n equals, to get my x to the n plus r, I end up with n equals 1. And then it's kind of weird. Like, how would I, do you know how I'd approach that?
Right. Remember, we talk about one example with separate cases. We deal with the case when n equals 0 separately, when we encounter this situation. You do n equals 0, what happens? You just evaluate when n equals 0. In this case, you say when n equals 0, you have r, the first term, you have 3 times r minus 1, a0, x raised by r, right?
Yep.
Your first term. The second term, you do the same thing. You evaluate n equals 0 separately.
Okay.
Sometimes you encounter, right, if you encounter n plus r plus 2, you evaluate n equals 0, n equals 1 separately. Because we can always deal with finite terms, you know, individually.
Yeah. So, but I have another question.
Yeah.
Like, when I have the finite terms, and they're to like x to some power that's not the same power as it is in the sums, right? Because that's what's going to happen.
Yeah, right, exactly.
Am I allowed to just ignore like the sums or ignore the terms I've taken out and set them equal to 0, since like it's technically, you know, like it's like with partial fractions.
Okay, in general, right, for pure mathematics, we don't really care about the finite terms. But with life applications, it's different. So just in general.
I see. Okay. So in this case, we're readjusting, like the last one I just did one of them, I took out a finite term, but on this one we're doing the other ones and setting the sums of n equal 0 to n equal 1.
That's right.
Oh, okay. Thank you. I'm not sure if that answered Shinyi's question, but
yeah, thank you. Thank you.
You're welcome. You're welcome.
All right, thank you.
You're welcome. Good questions. Anyone else has any questions or any comments? $16, right? How many of you major in math? I think a lot of you probably major in computer science. That's the most popular one. Actually, my first master's degree is computer science. I heard a sound. I thought someone. Okay. Okay, so today we're going to talk about solutions for the two solutions of R. They differ by an integer. So basically, it's R1 equals to R2 plus some integer, or you know, vice versa. But previously, we see the two solutions of R is like 0 or 1 half, or maybe 1 or -1/3, things like that. But today, they differ by an integer, okay? And of course, regular singular points. So we have a differential equation like this, right? This is still our capital P. This is still our capital Q. Remember this initial equation. So we have done that, right? We have yeah, just we didn't see any presentation over this. But let's just recall a little bit. Recall we use this initial equation and right, we solve for R1 and R2, and R1, R2. I think R1 is the smaller one, R2 is the big one. So R1 minus R2 is not integer. So we have this real roots of initial equations. Junyi?
Yes, Professor. I just wonder, like, I'm curious about that. Like, if we're solving, like, we're trying to solve the R1 and R2, is there any way we will get the imaginary roots of that?
Imaginary roots, because for the purpose of studying those each method, we made the questions perfectly fit into the situation. Not for now. Not for now.
All right, thank you.
Okay. So if those two the same, we get perfect squares, right? We only have one solution. So when they differ by an integer, we use this capital N to represent. Then there may or may not be two linearly independent Frobenius series solutions. So we're going to talk about two kinds. One is called a non-logarithmic case, and the second one is logarithmic case. So for a situation like this, for the two R's differ by an integer. So let's see this example. Right, we still have a y prime, b y double prime, b y prime, and c y form equals 0. And we want to make a p of x, q of x form. Then little p is multiply x with a capital P. A little q multiply x squared with a capital Q. So we get a p as a linear function. We get a q as a linear function. So of course 0 is in the domain. But because we're talking about a solution with a power series, so we use a word of analytic, which means 0 is analytic for P and Q. So the initial equation, we have this R times R minus 1 plus 3R. Right, we solve, we get two integers. And two integers, of course, differ by an integer. So we are just thinking a solution to be, in this case, y as a power series, the leading term. The leading degree is n plus r. Then we find a y double prime. Y double prime is a power series of this. And y prime, power series of this. And y is just this one, right? So we substitute into this original equation. The same trick as before, right? We simplify. We're trying to match up with the same degree of x, same exponent of x. And in the end, we get this one to be the coefficient of x raised by n plus 1 minus n plus r minus 1. And this one is, with this, is the coefficient of the variable with n plus r. So we ignore the n equals 0 term, reindex this, starting from 1. In that case, we can match up those two exponents of the variables. Then when the summation is 0, that means all the coefficients adds up to be 0. For n equals 0 case, right, because we reindex this, the thing basically ignores the n equals 0 case for this one. So we deal with it separately. So that equals to, so n equals 0, we have this, that's this. And then we have r equals 0, remember the two solutions, 0 and -2. We have 0 and -2. So in either case, we get 0. Right? We get a 0 for this. So that is to say, the first term of C naught is just, it just can be any arbitrary number, right? Because this 2 is 0 for r equals 0 or for r equals -2. So C0, C naught can be any number. For the rest, so n greater than or equal to 1, so we have this. And we're trying to find a relationship between two terms. So if we start with R2, the solution of R is -2. So what do we get? We get this, right? We could see Cn and the Cn minus 1 term has such a relationship. And if n not equal to 2, because if n equals to 2, we get 0. Cn minus 2 is a common factor of those two. So if n is not 2, we get a relationship between the current term and the previous term with 1 over n, right? The scalar of 1 over n. N equals 1, if n equals 1, we have C1 equal to C naught from this. If n equals 2, right, this is 0, this is 0. And we cannot see much about this too, right? C2 and the C1, because we have those two terms as 0. For n greater than 2, we have this, general term. So Cn can be represented with 1/n of the previous term. We can evaluate some of them. So if n is 3, we see C3 equals 1/3 of C2. N equals 4, we have 3 times 4, 1 over 3 times 4 of C2. 5, so on and so forth. Right? If we multiply 2 in the numerator, so that means we multiply by 2 in the denominator. So we would have a 2 times 3 times 4 times 5, which is 5 factorial. If we do the same for here, C2, if we multiply 2 with C2, we would have 2, 3, 4 in the denominator, which is 4 factorial. So for n greater than 2, we see the nth term with the C2 term, right? Because we started with 2. We started with n greater than 2. We start with 3 for this case, right? But then 3, the term 3 and term 2 has such relation. So in the end, the nth term is 2 over n factorial of C2. So we have this nth term representation. So, this. So we have, if r equals -2, we have such solution. So C naught and C2, right? Because we have a C0, C1, we didn't get anything, right? Because we have this Both are 0 terms. C0, we did get something. So C0 have this x raised by -2, 1 plus x. Then for the terms greater than 2, we get such representation. This is for C2. And this multiplied this is for terms starting from 3. Anyone has any question? So we have two linearly independent solutions, one for -2. So y1, y2, and y2 we can write as this. Because y1 is for the solution R to be 0. Notice we haven't found the Frobenius solution corresponding to the larger root R1 equals 0. However, if we did solve for the coefficient corresponding to R1 equals 0, we would find series y2. So now let's see an example. We don't get two linearly independent Frobenius series solutions. Let's see this one. We have x squared, y double prime, -x, y prime, x squared minus 3y equals 0. So dividing by x squared, we get into p, q form. Then we multiply x with capital P, get a little p. P of x is a constant function. Little q of x, multiply x squared with capital Q. We get a quadratic function, x squared minus 3. So P of 0, 0 is in the domain of both functions, or we see 0 is analytic for both of them. The initial equation is this. You will plug in, and then we solve for R. We get two integers, so they two differ by an integer. So we use a solution of y, in this case, x raised by n plus r. Of course, we found a y prime, y double prime, similar as before. We simplify. In the end, so we see this one, we have r plus 2. We reindex, then we deal with n equals 0, n equals 1 separately. And now we lined up this, so we can factor out this. Because x raised by n plus r, x raised by n plus r, that's what we want. So when n is 0, we get an initial equation like this, because it's c naught equals 0. And if n is 0, get this one. So this is r minus r. Oh, hold on 1 second. Oh, r minus 1, r times r minus 3. So what do we get from here? R squared minus r minus 3 equals 0. So why this equals 0? No, oh, sorry. Oh, hold on. Type O again. Yeah, Rx negative 1, 3. Negative 1, 3. Yeah, that's a type O there. There's no, oh, the R, okay. R minus 1, R minus 3. Oh, yes, it's the same. It's just this R, written in the back here. Yeah. So when n equals 0, yes, so we have this C naught. This equals 0. So, either this is 0. So when this is 0, C naught can be any number. If n equals 1, what do we get? We get this, The C1, we'll solve for C1. We simplify. We see for R equals to -1. You can plug in. That's 0. That's 0. Let's just, so C1 equals 0. You plug into 3. It's the same, right? For n starting from 2, we can find, we're supposed to find a relation between Cn and Cn minus 2. So let's check with root -1. Use the -1. We just plug in -1. Plug in -1. So we have this simplified to be this. Then this we can rewrite as Cn equals to -1 over n times n minus 4 Cn minus 2. So we found a recursive relation between nth term and n minus 2 term. This is for n starting from 2. And of course, not for n equals to 4. So since C1 equals 0, so all the RCNs equals 0, right? You can go back to check from the equation above. For n equals to 2, so we have C2 equals to 1/4 of C0. When n equals to 4, we cannot do that because n minus 4 is not, the denominator will cause it to be 0. So there's no way to choose a C0 to satisfy this equation. So because of this situation, and it says C0 cannot be 0, right? So then there is no Frobenius series solution corresponding to the smaller root of R equals -1. Anyone has any question? Okay, now let's check R equals to 3. When R equals to 3, we simplify. We get an nth term with a relation -1 over n plus 4 Cn minus 2. We have no problem with, so for n starting from 2 again. Because of C0 is 0, so all the other ones still 0. So we only care about the even term. So when n equals to 2, we see that's 1 over 2 times 2 plus 4, 6, right, of C0. When n equals to 4, we have this, we have the positive 2 times 4 times 6 times 8. When n equals to 6, we have 2, 4, 6, 6, 8, 10. So we have 2, 6, starting with 2, 6. Now this one added 4 and 8. And 2, 4, 6, 8, this one added 6 and 10. Because every term will have n times n plus 4. So alternating, so -1 raised by n of C0, we have this up to 2n, then 2n plus 4 terms. So this is in 2 times 4 times 6 times 2n. That's 2 to the nth power of this, or 2 to the nth power of n factorial. Right? Because each one we can factor out 2. Each one has a factor of 2, so that's a 2 to the nth power. Then the rest will be 1, 2, 3, since we factor out 2, is the n, so that's n factorial. And for this pattern 6, 8, 10, 2n plus 4, we can also factor out 2 from every factor, so that's 2 to the nth power. Then we're left with 3, 4, 5, and n plus 2. And this one we can add. That's n plus 2. N plus 2 minus 3 plus 1, still n plus 2. And then divided by 2. N plus 2 factorial divided by 2. Right, because we don't have 2 here. So there's 2, 3, 4, 5, 6, so on and so forth. So after n plus 2 factorial. The only thing missing is 2. So that's why we see here divided by 2. Or we can write as 2 to the nth power minus 1 times n plus 2 factorial. So similarly for this, right, factor out 2, we have a 2 to the nth power, then factor out 2 from here 2, but here we're missing 4 and 2. Right, so that's why when we do this, we have a 2 to the 2nth power minus 1. So all the 2's as factors in here. And the rest will have n factorial and n plus 2 factorial. So C2n is in a relation with C naught, the first term with this alternating series. So the Frobenius series solution can be written as C naught x raised by 3, because R is 3 now, 1 plus this n starting from 1, negative 1 alternating series, x raised by 2n. Then the rest is just this, right? Do this. Anyone has any question? Yes, David?
Yeah, could you remind me why C of 1 was 0 again?
C of 1, oh, is a plug-in. We go back to the equations.
Like, see the C of n where it equals negative 1 over n minus 4? Yeah, that one.
This one, right? Yeah.
So you plug in n equals 1, and then...
You plug into this initial equation.
Oh.
Right?
Okay.
For the other terms, because of the two solutions. Yeah.
Sorry, I missed that.
Okay, great. Anyone else has any questions? All right. So when only one Frobenius solution exists, we need a way to find the second one, second linearly independent solution. We do this through the method of reduction of order. We will use the fact that knowing one solution of y1 to reduce a second order differential equation into a first order differential equation. Let's see how do we do that. So suppose we know y1 is a solution to this form of differential equations. And we can see y2 is in the relation of y1 with this v of x as a scalar. So if we can find such a v of x, then we know y2 is also a solution. So let's see y2 is v of some, just some function of x, y1 x. Then y prime will be this product root, y double prime, product root again. So I have 4 terms. So simplify this a little bit, right? So we get back 3 terms. Then we plug back into our original equation. So we get this. If we regroup in this, so let's see, we regroup with this. Y double prime, P, Y prime, Q, Y. With this V double prime, because this, again, you see, we have in the form, PQ form. And the rest is just V prime, v prime y1, v prime y, but this one with some p of x. This is v double prime. So basically, so we want to form something like this. So y1 is the solution, so we have this one equals 0, right? Because y1 is the solution, so this one is a 0. So we're left with the rest of this to be 0. And this is in the form of v double prime y1. This one we have y prime, we have v prime, we have v prime, right? So it can be written as this. So I have a v double prime and a v prime. So let's see, let u equals v prime. So the equation becomes u prime y1 because we have a v double prime, right? V double prime, now it's just u prime. And then this is 2y prime, p of x y1, so v prime becomes u. Remember this kind of equation of something prime, something self, right? We have a u prime and a u equals 0. So we can use the integrating factor for this equation, right? The integrating factor is such a rho is e to the integral of this, right? So integrating this, integrating factor, dx. We simplify that, in the end we get this y1 squared e to the integrating px. So we have this y1, 2 with this integrating factor u prime, and just plug in the integrating factor into the original equation, into this. We simplify, then we see this one, just this one. That takes a little bit of calculation for you to do this, to convince yourself this one, it is this one. So integrate both sides, integrate this side, integrating of 0 is some constant. Integrating this side, we just have this. Then we solve for u, so e equals to this, right? And then we set up u as v prime, so that means v prime equals to this. We integrate it again to get back a v, because we want to solve for v. Get this. So if we write a v as, remember y2 equals to y1 times v, or y2 equals to v times y1. So that's to see v can be written as y2 divided by y1. And so y2 divided by y1 is this v. Then y2, we just multiply y1 to the other side. So y2, our second solution, can be written as a constant times the first solution, integrating this divided by y1 squared dx. Anyone has any questions? So this is called a reduction of order. So this is new to us. Okay, so this reduction of order approach is used to find the second non-Frobenius solution described in the next theorem, the logarithmic case. So the above one is a non-log case. So this one is log case. So let's see this form again. So we have this capital P, capital Q form. Under the assumption the two characteristic solutions differ by an integer, a positive integer. So we assume again we already found the first solution. Is this case, right? You can write as x raised by r1, or you can just do here x raised by n plus r1, because sometimes the nodes, you know, written in this case, sometimes the nodes written in this case. So we want this a not equal 0 for x greater than 0. So theorem. Suppose x0 is a regular singular point, right? Which means this little p, little q, so which means 0 is in the domain of those both. Suppose x0, suppose 0 is a regular singular point for such equation, differential equation. And rho greater than 0 be the minimum of the radii of convergence of this and this, right? So let R1, R2 be the real roots of the initial equation. So, okay, we have this initial equation with R1, R2. So this probably is a type O again. If R1 equals R2, then the two solutions Y1, Y2 are of the form this Y1 equals to this for the A naught and not to be 0. For the second one is Y1 of x times log x plus x raised by R1 plus 1. You can put over here, or you can just add to the exponent of x. Okay, sometimes it's written in both forms. So this Bn x raised by n. So if R1 equals R2, all right, then the two solutions are in this form. Y1 is such, and Y2 is this term with a different coefficient with the exponent plus just one more, right? Because x raised by R1 plus 1 plus n. So one more than this. So those two terms are quite similar, except the coefficient. So what's totally different is this one. It's log x times y1, y1. So if they differ, if the two r's differ by a positive integer, yes. So in this case, r1 is bigger. R1 equals r2 plus positive integer n. So y1 is in this case, right, same thing. We wanted the first term not to be 0. And y2 have something similar. This is x raised by n plus r2 with some different coefficient, and with this log term, log x times y1. Then the difference is we have this c. We have some constant. If those two are the same, we don't see c here. There's no constant here. Just y1 and the log x. But if they differ by a positive integer, so we have this constant c and times y1 times log x. So notice c can be 0. So in which case there are two Frobenius solutions, right? So if c is 0, we see y1 is this, y2 is this. There are two Frobenius solutions. The radii of convergence of power series in this theorem are at least rho. The coefficients can be determined by direct substitution. So this is the theorem, right? So these two cases, if the two solutions are the same, we have those two solutions. If the two, so those two solutions are the initial equation solutions. And those two solutions are the solutions of the differential equations. If these two are different by a positive integers, we'll have those two. With those two solutions. Let's see some examples. So we want to find out the second solution of Bessel's equation. Bessel's equation, right, of order 0. So recall R1, R2 equals 0 for this equation we did before. And so we can write Y1 is in this form, Y1 in this form. So this is from the calculation of before. And since in these two, if we do the initial equation, we can find out, oh, we already did this, R1 equals R2, right? Since those two solutions are the same, we just follow this. So Y2 is log X times Y1, and this is X raised by R1 plus 1, R1 plus 1 times this power series. Or you could just ignore this one, add the power R1 plus 1 into this, N plus R1 plus 1. Since R1 equals 0, right? Since R1 equals 0, so this is just in general. For since R1 equals 0, so we have N plus 1, right? N plus 1. And Y2 prime, we can differentiate this. So we get this. Then we differentiate this again, we'll get Y2 double prime. I think for you it's worthwhile to do the calculations. Substituting back into this because we want to check if it's indeed a solution. So substituting into this, the original differential equation, some tedious calculation. I'm going to skip connecting like terms, simplify collecting like terms. But Y1 is a solution to the equation, so we have this, because this one, so factor out, right, for ln x, so that means this is 0. So we're left with the rest of the terms. This is x raised by n, this is x raised by n, but this is x, this is x raised by n plus 2. Y1 is in this form, Y prime in this form, Y x times 2x times, so we get this one. Plug back in some tedious calculations. Keep calculating. So the only term involving x in this equation is a C1x, right? C1x, because this is x raised by 2n. This is x raised by n, but this is starting from 3. So on the other side is series 0, so we get C1 equals to 0. So all other powers come from x raised by n, right? Because this is x raised by 2n. So we have this n2cn plus cn minus 2 equals 0 for r terms. Then for n equals odd, we have this relation. The nth term with n minus 2 term with this minus 1 over n squared as a scalar. Since C1 equals 0, so all the other coefficients are 0. Now let's see C2n. Right. For this one, for this term, C2n. So get this one is 0, C1 is 0, so this term is gone. Right. Talk about this. And this one we do have a x squared term. But then this is x raised by 2n. When equals to 1, we have this x squared term. We have this x raised by 2. So this is for n equals 1. So from the calculation, we get n C2 equals a quarter. Then for n starting from 2, we simplify some tedious calculation, so we get such representation. So what do we get? We get a C2n minus 2 term, right? So C2n, so the 2n term and the 2n minus 2 term has such relation. For n equals to 2, for n equals to 2, we get a C4. We calculate, we get a negative 3 over 128. For n equals 3, we get such a big number. So for this case, it's difficult to form the n's C. So this is C2n. Right. So write out a couple of terms. So the solution 2 is in the form of this. Well, this is G naught. If you don't want to use it, you don't have to use it. Sometimes mathematics is just a lot of notations. Remember the G naught. Just y1. Okay. Just the first solution. Just ignore the G naught. So just y1 times ln x. Right. Remember also in the theorem, if the two r's are the same, r1 and r2 are the same, we have y1 with the first solution multiplied by the log term, log x, then plus some, infinite series. So we can write out a couple of terms here. Otherwise, just write this C2n. All right. Pretty complicated representation. Anyone has any question? Oh, that's it. That's it. So what's new for us? So the two kinds of new solutions. One is a log case. One is a non-log case. With a log case, we have this theorem. For the two solutions are the same, or for the two different binary integer. Okay. With the two different binary integer, we have this C. So let's start with this. So if the two are the same, we have this, the first solution multiplied by a log. Then with this, right? So the b and x raised by n plus r1 plus 1. And if the different binary integer, so those two are pretty similar, but this one is x raised by n plus r2. And this term is y times log x, but with a number c. So that's log case. Non-log case, excuse me. Non-log case, we're thinking, so we have a solution y1 already. We're thinking about second solution is y1 multiplied by some function of x. Some function of x. In the end, we get this equation. We get this differential equation which we can apply integrating factor method to solve for the equation. So in the end, usually we get a second solution in this case. In this format. So next class, hopefully some of us can present some questions similar to this. Anyone has any questions? So I think only those two things are new to us. The calculations, finding the recursive relationships among terms are very similar, as before. Anyone has any questions? Okay, if not, that's it for today. If you don't have no questions, you're free bird for tonight. If you do, I'm still here. Yes, Junyi.
For my question, it's just beside the homeworks. It's about my presentation grades. I just want to confirm with you. Yes. Can you double check? Like, I think the shared files have all my works and like all my presentation done before. I think like I saw it like there will be like 7 of them where the it says math 2206 and the numbers behind next to it. They're all my files, and it should be like there will be like 7 of them. Can you just update my grade after if when you're available? It's like to 70 out of 100s, please.
For Junyi, what I remember is maybe 2 times your presentation. Remember you didn't finish, so you finished the next one. Remember that?
Which one?
I don't remember which one. I remember that when you presented something, you were confused. You were not able to make corrections.
No, that's not me.
Oh, that's not you?
That's not me. I didn't do any confusion for my presentation. So only for one happens. Yeah, if only one happens. I remember the one that the one that only present for the modify is the homework 11. I think because of someone already presented that questions, and I do the modified one. So back then.
Yeah, because you cannot depend on the recordings over there. Because this is what happens. Sometimes sometimes I point out your mistake. If you're not able to make corrections on the spot, ask to do next class. So so that's why the files there is not 100% dependable.
Yeah, I understand, but like, I remember all my presentation already like completely done for it. Like not like you weren't asking me to do next day. So
I see. So you're saying you have 7, but here only recorded 5.
Yes.
Okay, let me check. Let me check my notes. All right.
Yes,
Let me
please.
double check my notes. Okay. All right. Anyone else has any questions?
Yes, Professor. I have a similar question to Junie as well. Because for the presenting, mine says 4. And I was like, well, I'm pretty sure I presented more than 4. So I wanted you to help me check.
Susan. Okay, I'll check yours.
Okay. Thank you.
You're welcome.
Have a nice night, Professor.
You too. Have a good night.
Good night.
Good night. Yes, Lisa. Liz.